I would like to repeat that here we get the heat operator, and in this operator we see a part which is equal to the differential operator D. We considered this differential operator and its modular correction in the previous lecture. So from this point of view, the heat operator H is a generalization So heat operator generalizes this differential operator which we used in the case of modular form in one variable. And this additional part in the heat operator related to the latest part, to the all abelian variables of Jacobi form. Now let's analyze the action of the heat operator on Jacobi forms. We consider a Jacobi form of weight k for the lattice L. This function has the following Fourier expansion. N is a natural number and L is a vector from the dual lattice. Moreover, we know then the indices satisfy this condition on the hyperbolic norm of the index. The hyperbolic norm of the index is greater or equal to 0. If we apply the heat operator H on this function, we get the additional coefficient 1/2, the summation, and now I have to use the fact which we discussed in the beginning of this lecture. So in our case, the lattice M, this is the lattice U plus L minus 1. This is our lattice L. And this fact gives us the hyperbolic norm as coefficient in front of any Fourier coefficient A and L. Certainly this is not a Jacobi form in general, but nevertheless, after the action of heat operator, we have a similar Fourier expansion. It means then we still have this condition. Moreover, we have now a stronger condition. Then the hyperbolic norm is strictly positive because we cancel by the action of operator H all Fourier coefficient with 0 norm. In particular, let us assume then phi is a Jacobi form of singular weight, the minimal possible weight for the lattice L. The rank of L is equal to N0. For example, we constructed such Jacobi forms for the lattice D8, E8, and so on. We know then if the Fourier coefficient with index NL of this function is not equal to 0, then the hyperbolic norm of its index is equal to 0. Therefore, such Jacobi form of singular weight belongs to the kernel of the Hit operator. In this case, certainly the image of the Jacobi form is Jacobi form, but this is trivial Jacobi form, 0. But nevertheless, you see that if we compare H, the Hit operator, with the differential operator D, which we use for the usual modular form, then we can compare Jacobi forms of singular weight with constant, because constant belong to the kernel of the differential operator D. And now I would like to construct a modular correction of this differential operator H, because the modular correction of the modular correction of D is the modular operator dk, equal to D plus 2k times G2, the multiplication, the operator of multiplication by G2, and this modular differential operators transforms modular form of weight k into the space of modular form of weight k plus 2. I would like to construct a similar modular differential operator for the Hit operator. But to construct this operator, we need some transformation formulas. Now, we are ready to discuss the formula of the transformation of variables in the Hit operator. I would like to consider the Hit operator in the new variables tau tilde and z tilde, where as usual a, b, c, d as an element from the modular group SL2. In the blue color, I remind you the formula for the transformation of variable if you would like to change and you would like to consider our new variable to tilde and z tilde in terms of the old variables, you have to use the Jacobian matrix to the power -1. So this formula gives us the following relation. This is simply the new differential, the new covectors written in the term of the old covectors delta over delta tau and d over delta over delta z e. This elementary formula you can get without any problems at all. So only I have to add one additional bracket here. Now, using this transformation formula, we can write down the Hit operator H in new coordinates tau tilde and z tilde. So these formulas, in principle, you can find, and it's very similar to the formulas in the theory of integrable model. So, and if you change all the variables, you get the additional term which comes from this additional term. The additional coefficient, 1 over 2 pi I, comes from the fact that we take this part in the heat operator with coefficient 1 over 2 pi I. Now, using this formula, I can prove the following proposition. This formula is true for any matrix M from S, L to Z. In particular, if phi is a Jacobi form of weight K and index L, for example, weak form, then this action gives us the original function, because this is exactly the modular functional equation of Jacobi form. So, if you analyze now this proposition follows from this formula. This is direct corollary from this formula, and you see that in the action of the heat operator on Jacobi form, we have the second term closed to the modular transformation of the quasi-modular Eisenstein series. Therefore, if we act on Jacobi forms by the heat operator, we get very correct action, and we have additional term related to the quasi-modular correction. But now, let's assume that N0 minus 2K is equal to 0. This is equivalent to the fact that N0 is singular weight. It's better to write down this is K is equal to N0 over 2. Therefore, for the singular weight, this formula is true. You can compare this argument with the arguments we used for modular function of weight 0. In this case also we can consider meromorphic function or function which are not holomorphic at infinity. And for the singular weight, the heat operator is modular operator. Let me fix this conclusion. For the singular weight, the heat operator H is modular differential operator, because this operator commutes with the modular action.